Noise cancellation headphones are marvels of modern engineering that revolutionize the way we experience sound. They can create a private universe of audio, offering an escape from the bustling world around us. But what is the science behind it? First, what does noise cancellation even mean? In headphones, noise cancellation can be broadly categorized into two types: passive and active. Passive noise cancellation is achieved through the physical design of the headphones, like the seal they form around your ears. Active noise cancellation, on the other hand, involves technology that actively counters external noise, often through anti-noise sound waves. But how does it work? Active noise cancellation technology, as used in Apple headphones like the AirPods Pro or the AirPods Max, is a sophisticated system that involves several components and processes. These headphones are equipped with external microphones that detect ambient sounds from the low rumble of traffic to higher-pitched office chatter. But what does this even mean? Sounds are vibrations that travel through the air or other mediums like water or solids as sound waves. These waves are created when an object vibrates, causing the air around it to move. How? A vibration is a mechanical phenomenon whereby oscillations occur about an equilibrium point. An object vibrates when it's subjected to a force that disturbs its equilibrium. This disturbance can be anything from a physical strike, like hitting a drum, to sound waves hitting an object, like vocal cords being moved by air passing through them. When disturbed, the particles in the object are displaced from their rest position. Once the external force is removed, the object tries to return to its original state, but due to inertia, it overshoots and moves beyond the equilibrium point, creating a vibration. As the object moves back and forth, it pushes against the air particles next to it. This causes these particles to move, which then bump into the particles next to them, transferring the energy along. This movement of air particles creates areas of high pressure or compression and low pressure or rarefaction as they move. These alternating high and low pressure areas move outward from the source of the vibration, forming sound waves. The sound waves spread through the air or any other medium as the particles transfer the vibration energy from one to the next. The speed of this energy transfer, and hence the speed of sound, depends on the density and elasticity of the medium. When these pressure waves reach our ears, they cause the eardrum to vibrate, which is then translated into electrical signals by the inner ear and interpreted as sound by our brains. When a sound wave hits the microphone, it causes a diaphragm inside the microphone to vibrate. This diaphragm is a thin piece of material that moves back and forth when impacted by sound waves. Attached to the diaphragm is a coil or other type of transducer element. Transducers convert electrical signals into usable direct current or voltage that can be easily measured. So when the diaphragm vibrates, it moves the coil in a magnetic field, creating a varying electrical current. In addition to external microphones, there are also internal ones that listen to the sound reaching the listener's ears. This helps the system understand what portion of the external noise is actually making it through the noise cancellation barrier and adjust accordingly. The core of ANC lies in the noise canceling circuitry. This system takes the sound captured by the external microphones and analyzes it in real time. It then generates a sound wave that is the exact inverse or antiphase of the detected noise. This is a key aspect of signal processing. A phase designates a point in a sound wave cycle and is also related to frequency. When two sound waves are in phase, the result is increased amplitude. When they are 180 degrees out of phase, they can completely cancel each other, resulting in little or no sound, which is what the active noise cancellation system does. The generated antiphase sound wave is played through the headphone speakers along with the user's audio. When this sound wave collides with the incoming external noise, it effectively cancels it out through a process known as destructive interference. This significantly reduces the overall noise level. Apple's ANC technology often includes adaptive algorithms that continuously monitor the external environment and the fit of the headphones in the user's ears. These algorithms adjust the antiphase sound wave in real time to optimize noise cancellation for changing conditions. However, the active noise cancellation headphones is more effective in handling lower frequency noises better than higher frequency ones. This is due to the inherent characteristics of sound waves and the technological limitations of ANC systems. Lower frequency sounds, such as the rumble of an airplane engine or traffic noise, have longer wavelengths. These sound waves are more consistent and less complex in their pattern, making them easier to predict and counteract. ANC systems work by generating a sound wave that is the exact inverse of the detected noise. The simpler and more consistent pattern of low-frequency sounds allows the ANC system to more accurately and effectively generate these sound waves. High-frequency sounds like human speech or high-pitched beeps have shorter wavelengths and are often more complex and less predictable in their patterns. This complexity makes it more challenging for ANC systems to generate an accurate antiphase sound wave. Additionally, high-frequency sounds tend to be more directional and can more easily find their way through small openings or imperfect seals around headphones, diminishing the effectiveness of the ANC. ANC headphones also rely on passive noise isolation, the physical barrier created by the headphone design, to block out noise. This physical isolation is generally more effective at blocking higher frequency sounds, but there's a limit to how much can be blocked based on the headphone's fit and seal. Imperfect seals can let in high-frequency sounds more easily than low-frequency ones. The ANC system also needs to quickly generate and emit the antiphase sound wave. For low-frequency sounds, the slower wave cycle gives the system more time to react and create the inverse wave. With high-frequency sounds, the faster cycle means the system has less time to respond, making it more difficult to achieve precise noise cancellation. In addition, our ears and brains are more sensitive to changes in lower-frequency sounds. Thus, reducing low-frequency noise is often perceived as more impactful in improving overall listening comfort and experience. Many of Apple's headphones also offer varying levels of ANC, allowing users to adjust how much external noise is canceled. This can be especially useful in situations where complete noise isolation isn't desirable, like when you need to be aware of your surroundings. The effectiveness of ANC greatly depends on the speed of processing. Apple's headphones are equipped with powerful processors capable of performing the necessary sound analysis and inversion almost instantaneously, making the noise cancellation effect seamless. While ANC technology is very effective, it does have its limitations and the technology is constantly evolving, with newer models offering improved noise cancellation across a broader range of frequencies.